In this video we're going to look at interference from 2 point sources. It could be a longish video, so you might even have to go back and rewind because there are a lot of tricky concepts within this. The basic level of understanding is okay, but when you're getting into the details, if you're after those merits and excellence, those top level answers, then the details are vital. So a point source, first of all, is a source of waves that comes from a single point. So you might think of throwing a stone into a pond and then wave fronts radiating outward from where that stone hit. Okay, so that's one point source. There are a number of situations in nature which we can model as point sources. That is, we can assume they're point sources. One of them is the situation I've got drawn over here, where we've got water waves approaching a barrier system, and the wavelength is the same spacing as the gap in here, so that is also a wavelength. So we're going to get the maximum amount of diffraction through each of these two gaps, and it's, in case you wondered, this is 2 point source interference because we're dealing with 2 points. You can have multiple points, but that's at a level 3, that's a little bit higher. So what are we going to see? First of all, we would consider one side and then we'll consider the other. So coming out of the first side over here, we're going to see a curved wavefront, and it's perfectly curved because of that gap being the same size as the wavelength of the approaching waves. So that means we're going to have curved waves radiating outward from the front like so. Okay, I'll draw one more. It gets harder to draw the further out you go, and it's harder to maintain that consistent wavefront. So if I'm drawing this by hand and I'm a little bit out with my drawings, please do your best to imagine what it should look like. I'll tell you what it should look like too. But I think it's more beneficial for you to see the construction as I'm doing here rather than just to plonk a picture down in front of you. In fact, even more beneficial is to do the construction yourself. So this is going to be the first video where I give you some homework. Your homework is to go and draw this and do the construction. You will feel a great sense of pride in your work, I hope, once you've done this, because it's very beneficial, and you'll hopefully develop a better understanding too. So now that's one side. We're going to consider the other side now. I'm going to try and draw as equally consistent, wavelength apart, wavelength apart. Okay, I'm flagging just a little bit. Let's see if we can. Not too bad, not too bad. Okay, everything should be perfectly symmetrical. There's a cool little pattern starting to develop where they cross over. They can radiate out further, but we're not going to. For the sake of this, we've got enough. Now, this is where we tie together superposition as well. I'm going to draw red crosses everywhere where these wave peaks cross over, in one particular line anyway. So here's one point, here's another point, and here's another point. Okay, we can, yeah, I'll keep drawing them. There's another one here, there's another one here, and there would be another one further out here as well, if you can imagine the extra drawing. We're going to keep drawing them over here. There's one here, there's one here. Oh, I hit the one of the buttons, you probably can't see it, and there'll be one out here. Now, also in between these, remember a wave has both the up and the down parts, so we've shown the wave crests crossing over and adding with superposition to produce a twice as large part. Okay, so that's where we've drawn the X's on the twice as large part. But it's equally true that the troughs will add and produce a twice as low part. So we can draw an X on there as well. And what we're drawing is X's on the positions of maximum amplitude. Okay, so maximum amplitude will give us a very particular wave pattern. Okay, and there'll be one further out here as well. So you can see that there's 3 lines developing. I'm going to draw these lines in. 1, 2, 3, and we call these lines where the peaks meet peaks and the troughs meet troughs, we call them lines of constructive interference, which was that first part over there. And we number them going outwards from the centre, 0, 1, there's another one out here, 2, 3, and so forth, and this is also 1, 2, 3, and so forth. What you would notice, if this was light, we're dealing with water here, but if this was light and you had a screen set up here, and perhaps used photographic film with two very thin gaps that are similar to the wavelength of the light, you would see a pattern of bright fringes. Okay, so say you shone a red laser this way, you would see red spots separated out, and then on 2, and then on 3. Okay, so now that's part of the picture, that's the constructive, but we also know when waves are travelling there is parts where the peaks will cross over with the troughs of another one, and you'll cancel out. So let's go and find those spots. Those spots are going to be where a peak meets a trough, so that would be right here. I'll draw them with dots, this one. There's another one right there. It's basically following along one wave front, and every time that it's not, or halfway in between, every time that it's not touching another peak, and it's halfway in between two peaks, you can draw. Okay, I just had a little hit a button and something happened, so I'm going to repeat that last part. Hopefully you're not bothered by that. So we were drawing lines where peaks meet troughs and they cancel out, and that's what this first green dot is. Second green dot here, third green dot there, and so forth. They'll just keep going out, and you can see there's this other line forming where peaks are meeting troughs, and that's lines where nothing will project on the screen if you're dealing with the light situation. And again on the other side, here, 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 where the peak is crossing over in between two other peaks, and again you get a nice line forming with nothing projected on the screen. You'd also get them outside here, and there's another line, and you can see that they alternate all the way through, and so forth. So there's our last line and another flat bit there. Okay, so that would be a line of destructive interference. So if these are water waves, if you were on a canoe or some sort of paddling device or just swimming, the lines of destructive interference would be the ones for you to walk, to swim down or to travel down, because they would be the calmest. They would be the easiest for you not to get chopped around by all the choppy waves, whereas a line of constructive interference is going to be massive peaks and massive troughs, going up and then down and then up, and that's going to be really hard. So it's going to be the rough, if you like, parts of the water. So where to from here? You will get three, I've mentioned light a little bit, but you'll get three common situations as a potential context for asking questions. You could get light, you could get sound, which we haven't talked about, I'll give you a quick overview shortly, and water. So we've looked at water, and but we need to also look at sound and light. No, we don't need to look at light because we've looked at light too. We can still represent, even though light doesn't really have these wave fronts like water does, we can still represent light in that same way and draw the same patterns. It's quite handy. But sound waves, if you imagine you substitute two speakers, so you put two little speakers in here, or you could actually do this. We've done it in class using cell phones, and we generated a tone, a constant single wavelength, because remember you have to have one wavelength of wave coming in. If you had a whole bunch of different wavelengths, like some Britney Spears music, or I don't know what the latest kind of stuff is, your latest music idol pumping out, you wouldn't get quite the same effect, because it's not all the same wavelength. So it has to be a single tone that's being generated, so monotone. And you would also, that's with the sound. With the water we've seen the wavelength the same. With light has to be monochromatic, a single chroma, single colour, like a laser. A laser is one colour, all in phase heading in. But anyway, you could draw the sound waves exactly the same and represent the interference patterns like this. Now there's one final thing to talk about with this, and that's just to list the factors which affect or which can be used to talk about. And there we've got the constructive factors. For constructive interference to occur, you have to